All right, as the first speaker, I also would like to welcome you to the second annual Data Science Conference at Rice. I'm actually on the paper review committee for this conference, so I can tell you have an exciting day and a half ahead of you. Also, I'd like to thank Jan and Keith for giving me the honors to be the opening speaker today. I work in Anadarko. We are an exploration and production company of about 5,000 people headquartered up in the woodlands. In the past few years, we've embarked on this digital transformation journey, trying to bring data scientists and the latest technologies to improve our traditional processes and workflows. Sounds familiar, right? And at the core of this transformation is the AID team, which stands for Advanced Analytics and Emerging Technologies. AID was formed in the beginning of 2017, as you can see from this timeline. The catalyst for the formation of this team was the new appointment to the board of directors. Sean Gurley, Silicon Valley entrepreneur, was appointed to the board in late 2015, becoming that voice of the latest technology at that executive level. And a lot of credit should be given to our leadership as a whole for being supportive of us through the creation of the team and of our R&D efforts right now as well. What makes our team unique and well-positioned for success is the demographics of our team. We have engineers and geoscientists in our team that come from the assets. They have experience working in an asset team, and they've been specifically selected to be part of the AID for their forward thinking and their vision of how to embrace and bring in new technologies to transform some of the traditional workflows and approaches. We'll also have a data science team that work closely with engineers and geoscientists to convert some of those ideas into the actual prototypes, a proof of concept solution, borrowing methodologies from most likely other industries and creating tools that we can get into the hands of users. And then we have a big data ops and DevOps component. Those are the software engineers that are able to take some of the prototypes and the proof of concept solution and convert them to enterprise-wide solutions, something that will become a permanent staple in a toolbox of engineers and geoscientists. As you can see, our team has grown significantly in the past couple of years, both in headcount and the project portfolio. In the middle of 2018, we feel like we've reached the critical mass of useful products that we've been working a lot on going out and doing stakeholder engagement with our end users, trying to show how some of these tools that we've generated can improve their workflows and processes. But later in 2019, we're going to focus on deploying a few solutions that we already have in flight and ready to become commercialized. So we think of this digital strategy as an enabler of our corporate strategy. Our corporate strategy can be best described as triple Ds, covering DJ Basin in Colorado, Delaware Basin in Texas, and Deepwater Gulf of Mexico. This is the backbone of our annual production of 640,000 BOE, or barrel oil equivalent, and a annual capital run rate of just over $4.5 billion. In the context of our corporate strategies, there's three digital focus areas. Advanced geophysical analytics to enable exploration success in Deepwater Gulf of Mexico. High-density subsurface interpretation to find new opportunities in lower 48. And digitizing operations with intelligence controls covering drilling, completions, and productions. So in a nutshell, we're covering U.S. offshore, U.S. onshore, and operations and productions. So now that we see kind of the overall goals of the company and the context, I'd like to zoom in and focus on one of the projects that contributed directly to one of our strategic focus goals for digital transformation. This project is called LogQC, and it focuses on well log quality control. So let me tell you what well logs are for those who may not be as familiar with the oil and gas industry. So as the well being drilled, there's a variety of tools that are being sent down the borehole. And they gather information at every half a foot about the subsurface as it passes through. So it gathers all these different readings, and you can see them from this table right here. Things like gamma ray, resistivity, bulk density, for each well that we drill. So you can think of it as a time series, but in a depth domain, essentially. Then petrophysicists are able to take these logs and these different readings and do what we call interpretation. From these readings, they're able to correlate to the actual rock type this corresponds to, and the properties that this rock type has, and pinpoint the presence of hydrocarbons and the quantities, if possible. So there are different combinations of readings allow for the better interpretation, and they're dubbed triple combo or quad combo, meaning that if you have all these curves available or these readings available, you get the best interpretation possible with the least amount of uncertainty. However, as we look at the lower 48 landscape, the well logs that we have are from the wells that were drilled 10, 20, 30 years ago, and so the data completeness is more of an exception to the rule. So it's very rare that you find a good set of triple combos covering the area of interest. So now let's take a look and see how this log interpretation fits into overall basin evaluation process in the lower 48. So first, you look at the area of interest and you try to acquire as many well logs as you can for the wells that were previously drilled, historical data that's available for that area. Then there's some data processing that happens and interpretation that actually pinpoints the different rock type informations in the subsurface. From that, you can build subsurface maps showing like what are the properties that exist at different depths. Putting it all together, you can create 3D volumes. And then geoscientists and petrophysicists and other petros can look at it and actually try to figure out where the next well should be drilled, most likely horizontal, because we've kind of used up all the pressure from the vertical wells. So now let's break apart this data processing steps into two. So we kind of look at the two more distinct steps, TOPS generation and log quality control and interpretation. So the TOPS generation piece, that's when the geologist will look at the logs and they will identify tops, basically identifying the boundaries for different formations. And you can see them shown here in different colors. Oh, now it works. You can see them shown in different colors in this cartoon. There's different formation types in the subsurface. So they create those tops or the boundaries and then they pass them on to the petrophysicists. Now, those guys do interpretation, figuring out the rock type and the properties, and then leading to the maps. However, before they can run their interpretation solvers and the algorithms, they have to make sure that the data that goes into them is actually clean and good, right? And you may be wondering, how can this data be bad? It's just a reading that's coming from the tool. But this is what defines our business problem. These logs are not always optimal, and this could be due to poor borehole conditions, acquisition error, or tool failures. Those abnormalities usually show themselves as gaps or abnormal spikes. As those go into solvers, they can produce bad interpretation of that result. So they have to be corrected before this data can be used. So in our model, so right now these things are corrected manually. And we'll talk about this in a second. But we came up with a model that can help us address this issue. So in this approach, we're essentially using all the good curves that exist at the depth as an input to our model, and the areas where the target curve has data as a response. From that, we create a model and then apply it in the areas where the response curve doesn't have any data to fill in those values. So a good analogy to think of can be like, let's say you have a movie, right? And those usually have at least two tracks, a video and an audio. And let's say you have an area where the audio is missing. So you can, from knowledge of what happened in the movie before and after, you can in a way create a model and then using the video as an input to predict what the audio should be. So this is kind of the same thing that's happening right now, but in a depth domain. So here's this traditional workflow that's taking place right now. So petrophysicists, before they can do interpretation, have to identify their data of interest. Then, taking all of the data that they want to use, they put it in the cross plots and identify the critical mass of data that's in good bounds, and then figuring out what are the outliers, essentially creating lower and upper bounds for each reading. And everything outside of that reading will be a spike that needs to be corrected. So for each type of curve, you know what the min and the max should be. So then they look at every curve for every log. Remember, each log has multiple readings, or the curves. And then they see whether, if it has too much bad data, if it's only a little bit of data present, they pretty much dispose of that log. They can't use it in their interpretation. If it has just a little bit of gaps in those unusual spikes, they correct it using some of the regression techniques, most likely just linear regression approaches, multi-linear regression approaches. So this is a very time-consuming process. It takes about 4 to 8 hours to correct a single log. So it takes a long time. And they have to do it for every curve, for all the wells. So here's our approach enhanced with the machine learning model that we've created. So there's still a couple of manual steps. The petrophysicists still have to identify the data of interest, put it through the cross-plots to figure out what are the bounds for each curve, where outside of it is abnormality. So we know what our cutoffs, as we call them, are. And then we also use zones, those tops generated by the geologists. Then they click run, and our automated ML approach starts. So the first thing is that in our approach, we're going to go and mark every point and every depth for every well as good or bad, creating what we call bad hole flags. So now we know where the good data that we can use for the model exists and where the bad data that we need to correct exists. Then we run what's called a single well model, so where each well is trying to heal itself in a way. It's going to see if it has enough good data to create a model and then apply that model to the bad areas. So each well has an opportunity to heal itself in a way, to try to self-correct. Then we re-examine all of our bad hole flags and seeing if everything has been fixed. If a well was able to correct all its mistakes, it's good, we're going to do the post-processing. If there's still bad hole flags left, or for example, if a curve was completely absent, a reading type was completely absent from a well log, we do what we call multi-well correction, where each well essentially will go around and find its neighbors and ask them for their good data. Using that good data of the neighboring well, it's going to construct a model and then apply that model to itself to correct all the bad areas. So then we are going to do some post-processing on our data, doing splicing of predicted values and original, and smoothing if needed. Then the users can review their data by either looking at the corrected logs in their softwares or look at the statistics that would generate during the correction. So this happens a lot quicker. So this process takes less than 2 minutes for each log to be evaluated through the single well and a multi-well. We are also working on automating this process of bad hole flag identification, so there's less manual input from the users needed. So let me just reiterate the importance of this problem and how much our approach contributes to our corporate strategy of enabling high-density subsurface analysis in lower 48. So as of now, petrophysicists are only able to use about 5% of the available data in a basin. Because it takes so long, it takes 4 to 8 hours to correct manually a single well. Therefore, we're looking at interpretations and making decisions in the presence of high degree of uncertainty. Essentially, you're looking at a large area and you're just having a few points define what that area represents. There's nearly not enough data to make a conclusive decision. So we're kind of flipping this equation with our tool, allowing petrophysicists to use 95% of the data for interpretation. So, because it only takes less than 2 minutes, and most of the process is automated, so they can correct a lot more wells and make them ready for their interpretation solvers. So now we're kind of looking more into this data-driven decision-making with much lower degrees of uncertainty, because a much denser data set is used to make conclusions about your area of interest. Okay, so this process was incremental. We started with algorithm identification. We tried multiple models, what could work best for our wells. We looked at the linear tree-based models, neural networks. We narrowed down on tree-based models based on the cross-validation experiments that we ran. Random forest data boost or gradient boost worked well. We give ability users to choose if they want to run one or multiple models. If they run multiple models, they can take a combined one, the ensemble of those, which seem to give better results. We also provide them with the opportunity to choose to run linear regression as well, just to give them more confidence in our tree-based model, because they're just less familiar with that. Multilinear regression, that's something they would have used, and if they see that this tree-based models perform even better than they would have done in their manual process, it just gives them that much more confidence in our approach. So let me show you the results. So here's the original image where we have a gap and a spike in a few curves. So after our single well correction, this well is one of those that has not as much bad data. We are able to fill in the gaps and put, with reasonable values for that range, and then, put the spikes into the bounds that they should be in. And they all go kind of smoothly with the rest of the curves as well. So if the bad hole flags weren't corrected with a single well, we do a multi-well approach. So let me walk you through an example. So let's say here we're trying to correct well A, and it has a little bit of data, but not nearly enough to construct a model to correct itself. You can't construct a model on 10% of the data to predict 90. It's not going to have good predictive power. And here let's assume that the blue one is the curve of interest that we're trying to recreate, and all the input curves are movie track in our analogy, are present for all the other wells. So all our inputs are there. So what well A is going to do, it's going to go around and find the closest wells it can and try to gather all the good data from B, from C. D doesn't have that curve at all, from E and F, until it gathers enough massive data to create a model that is able to fix the number of bad points that it has. So now we apply that model to correct well A. So here on the right, you can see an example where this track 7 was completely absent. Like we didn't have this type of reading in this well. It didn't exist. So we completely synthetically reconstructed this curve. So this was done by using only multi-well. There was no single well correction. This well was reconstructed by just creating a model from the neighboring wells. So we did some validation on our approach, and for our metric, we used the absolute ratio between the good point, between the original point and the predicted point over the accepted range. So let's say if your difference is 0.02 and your reading should be between 2 and 3, that's a 2% error. If your difference is 5 and your reading should be between 0 and 100, that's a 5% error. So kind of normalizing it to the accepted range. And what we see in our results is that the error that we get is well within the inherent tool error, meaning kind of like the noise that those tools generate as they go down the borehole. So here's some of the quantitative results. On the correction front, where we're doing actually single well correction followed by multi-well, meaning there is some data but maybe not enough, or maybe some curves are able to fix themselves with it. We did the 90-10 cross-validation, and so this is what's interesting. Let's take a look at asset 1. So it covers a certain square area, square mileage, and we're looking at about 300 wells in that square mileage. So the error that we get is between 5 to 10%, right? But then when we look at asset 2 that has about 5,800 wells for the similar square mileage, we're looking at a much smaller error from 3 to 5%. Which tells you that the more data you put in our algorithm, the denser your data set is, the better it performs. Because now each well, when it actually does go into multi-well, picks the wells that are closer to it and probably more similar to it in the properties of the subsurface. So it can create a better, more predictive models by looking at the neighbors when there's more of them and closer to it. We also validated how well we create synthetic curves. When there is no option for the well to try to self-correct, the curve was just absent altogether. So what we're doing, we're throwing away the curve, creating a synthetic curve, and then getting the error from all the good points. So our numbers are a bit higher. There's a lot more data is involved, and of course, because it's only multi-well. But petrophysicists did look at this data, and from their assessment, these curves do look reasonable. And it's better to have a curve that looks reasonable than no curve altogether. So we are in the process of prototyping, or I guess we prototyped it already. We have a tool already running using Google Cloud Platform, a virtual machine in a Google Cloud Platform. We're providing to the users a simple web interface where they can just type the basin name, and then the compute happens outside in the cloud, so their machine resources are still free. Right now, what we're looking at, the data still sits in our corporate databases, so there's still some latency for the data but we're aiming having a better marriage between the data and the compute all in the Google Cloud, and which should make it easier for the users also try to retrieve the data of interest as well. As far as how fast that actually runs, we were able to execute 5,800 logs from Delaware Basin on 14 parallel processes on our Google Cloud Platform VM in about 14 hours. So this was just allocated to us for POC, so resulting in an overnight process. Those virtual machines can be given 96 cores total, resulting in essentially a 12,000-fold speed up over the original manual process of 4 to 8 hours per well log. So it's a pretty good gain for the end users. So in the end, I'd like to just go through this journey of this project from the inception to where it is right now. So we have started with the ideation phase, and this is one of the earliest projects. This started pretty much, in early 2017 when the team formed. We started with the ideation phase, and we do allow that phase to take some time, even a couple of months if needed, because it's important to identify, you want to go on the right path right away and fail fast with all the little things that you try. But we started with the ideation phase, identifying the problem, how long it takes to correct the logs. And when we're looking at the high density analysis of the data, we're looking at 10,000 logs, so it's really not humanly possible to correct all those to do interpretation on them. So that was the problem. So as a result, we couldn't use all of this data in our interpretation and map creation and 3D volume creation. We did a small R&D proof of concept project where we took just 5 wells, and that's where we looked at different algorithms and figure out which ones work best. We created just a single well solution at that point. It seemed to perform well, so we quickly created a first prototype, essentially coding a plugin into a software that petrophysicists already use in their day-to-day work called IP, or Interactive Petrophysics. So it was just a plugin to their everyday workflow. It only did single well, and it ran on their local machines because that software ran locally. So there was definitely a limits on how much compute you can put into this approach. So they could correct about 20 wells in 2 hours. But what it gave us is user acceptance, like initial user acceptance. They were excited about what they can already do with it and kind of looking forward to what's coming down the pipeline when we started working on the multi-well. So right now, we already have a second prototype running using Google Cloud Platform VM on 14 cores, and that has a single and multi-well solution. The largest data set we're in is 4,800 wells. We are working with the asset teams to kind of help them put their data sets together and execute it as needed. But the final result is the enterprise solution. This is where the project is at right now. The DevOps team is working to create an enterprise solution, potentially maybe not even using the virtual machines in Google Cloud, but using other functionality, cloud function and messaging, that could pretty much give us a scale, as many wells as we have. Probably with these, it has a potential to scale up to the number of wells. So we could run 15,000 wells in a few hours, maybe even minutes. So I think overall, this project did a really good job contributing to one of our corporate goals of conducting a high-density subsurface interpretation to find new opportunities in lower 48. That's it. Any questions?
So your background is computer science, and if I look at this journey, what people, what type of skill sets in your company were involved at these different stages of it, and where did the expertise is, and how interdisciplinary is this thing?
So yeah, as you saw from the kind of the demographics of our team, all our projects, including this one, consists of a combination of a geoscientist, a data scientist, and somebody representing the DevOps. So from the very beginning, we're working together. From the inception, we have all different types of skill sets thinking about this problem. Of course, in the ideation process, there's a lot more weight That's in the hands of geoscientists for this project. But as the project evolved, like for the second state, that's where the data scientists are picking up most of the workload. And the geoscientists are just kind of testing it and making sure it performs well. As we start going to prototyping, that's where DevOps also start to get involved. But the key is that through the entire process, all the teams are aware of what's going on in all the stages. It's just the roles shift as the project matures.
Okay. So.
Do you ask Google to securitize all your information, or do you have your own cybersecurity platform that you work with?
So we work closely with Google, and we have a platform team that takes care of some of these details. But some of the VMs that we get are not your typical VM that you can, that you spin by clicking a button. They are customized to our environment. So that's another team that deals with them. And so, yeah, we don't use out-of-the-box components. We customize them to address some of our environment concerns.
Quick question. So when you talk about the multi-well correction, is that artificial intelligence kind of approach, or is it traditional?
Traditional machine learning. So, but except because the original well doesn't have enough input data, response input data to learn from, we have to go and construct that model from using other entities in our well.
Good. Now, if I compare that with other interpolation mechanisms, just like distance-weighted, traditional mathematical kind of way to do that interpolation, is that what the advantage you have there?
So, some of the traditional mathematical approach, that's something that petrophysicists have been doing in their manual correction using their softwares. And, I think that that may be more time consuming. We haven't tried to automate it to the fullest, but it's just automation as opposed to applying machine learning and stuff like that. So,
So my background is I'm a geologist and a statistician. So with a well log, you have different measurements being taken from different parts of the sonde. I know that you can have good quality data covering different depth ranges within a single well from different tools. So do you end up having a column of data for each log thing flagging what portions of it are valid versus other logs?
Yeah, so before we run our models, we'll mark all the data good and bad. And as you saw, one of the inputs into our model are the formation tops. So we actually don't just create one model for each well. We're zone those models. So that way, we're not learning properties of sandstone from another rock type. So we do a little bit of that.
So if I understand correctly, you're flagging what intervals for each log within each well are valid versus invalid?
We flag each depth. There's half-foot depths, and we say, at this depth, I have a gap. That's a bad data point. At this depth, I don't have a gap. That's a good data point. So I can learn from this one to predict this one. But then you have to gather enough of those good points to create a model for a given formation. We can talk about this later if you like.
Yep. Question in the middle left.
So for 15,000 wells, what's the recording frequency per single sample?
Half a foot. We're looking at half a foot, yeah.
And what's the average depth?
It's what?
What's the average depth?
Well, we have about 10 to 20,000 points. So that's divided by 2.
I had a question here. Are you able then to feed back some of the learnings from that end into automating the actual, front end of the QC process? Because there's still a manual part in the beginning, correct? Which you could, in principle, learn by feeding back instead of actually the manual labeling of what the...
Bad or good?
Yeah.
So yeah, as I mentioned, we are looking to automate the bad hole flag identification. In fact, this summer we had an intern starting on this project, and we're planning on including that piece into the overall tool. So there's less manual input from the user. So essentially, TOPS data comes from the geologists. They just have to identify the basin and click run.
2 more questions, I think. One over here.
Hi. So since the data is, well correlated, and you can predict, you can use one well to drive the estimation of its data based on multiple other neighboring wells. Is there a plan your downstream decision making will then be based on that synthetic well or partially synthetic well. However, it seems that your approach sort of extends to the whole volume in the area. Is there some plan maybe to not actually create individual well synthetic signals and just take the volume and use that in the downstream decision making with some probability distribution over whatever area point in the area they're interested in?
Well, since I'm not a subject matter expert, my understanding is that those volumes are created from the properties extracted from the wells. And I mean, as we do our correction, we're also, the errors that you saw are average errors, but we are providing users with the actual errors for each well, so they can, not use some of the wells that weren't predicted as good as the others. Right now, I don't think we have plans to actually looking at predicting at the volume level, but that's something to be considered as well.
One last question here.
So I'm a geochemist. In one oil sample, we collect thousands of compounds information, and this sounds like a great tool to combine that information. Do you have a plan to use this for other kinds of data, like geochemistry or other kind of physics?
Yeah, I mean, the data setup for this is, is pretty common. You have your input feature data and your available response versus having input and no available response. So if your data can be shaped into this format, all of these machine learning algorithms can be tried on your data type. It's just a matter of gathering, organizing your way in such a way that you have kind of sample data. It's possible, I think.
Well, join me in thanking our speaker again.